Okay, welcome back. And today we will be going over 11.6. If you check the title, it's called Absolute Convergence and the Ratio Root Test. So let's again start with reviewing. First, 11.3, we have integral test, which is pretty nice, but we require everything to be positive. 11.4, we have the comparison test. Again, we require everything to be positive. We say this is too restrictive, then in 11.5, we introduce the alternating series test. Here, you can have negative terms, but your negative terms have to be very regular. It has to be positive, negative, one after another. You cannot have random negative signs appearing at a random position. Okay? Then this happens when you have something like oscillation. You have positive, negative, positive, negative, positive, negative. So it's very useful. And then we say, hey, to check this, you just need to check two things. Number one, if the value is decreasing. Number two, if the value have a limit 0 when n goes to infinity. If it fails, we have inconclusive. So that's what we had so far. Of course, in general, for any series, your negative can be anywhere. You can have a positive term, negative term, followed by another positive, and then 3 negative, and then 4 positive. There's no guarantee they will be appearing in a regular pattern. Now, how do we handle this? If you think about what we have done so far in this class or in mathematics in general, we always start with something very small. We have the definition, and then we try to transfer them to be something we knew before. For example, we're trying to do series, but somehow we associate with integral, and then we can use every knowledge we developed before, so they're not wasted. Since we already developed everything we need to handle positive series, now to handle negative series, a natural thought is try to transfer it into a positive series. Okay, and then do whatever you need here. Okay, and then hopefully by doing some special operations, you will be able to transfer back. So it's almost like taking a detour. You have mixed sign, positive, negative. You transfer it to be all positive. Finish, and then find a way to transfer back. In general, this is not doable, only in very special cases. But let's see if we can do it. Now, if you have a sequence, if you have a series, let's say 1 minus 2 plus 3 plus 4 minus 4, you want to change every single term to be positive. We definitely know that. It's called the absolute value. Okay, no matter you put positive or negative in, they all become positive. Then this term here will simply becomes the sum n from 1 to infinity, the absolute value of an. Okay, up to now, everything is good. We change something negative sometime to all positive. Now the problem is we want to know the relationship between these two things. In other words, if this one converge, can we imply this one converge? Or if this one converge, can we imply this one diverge or converge? If we can build that bridge, then doing one can be done by transferring into another, do the other one. Okay, this is called the absolute convergence. That's what we're trying to establish with this. Okay, so let's take a note and try to see what do you mean by this absolute convergence. Okay, number one, it's a definition. A series is called convergent if this one is less than infinity. A series is called absolute convergent. Is the same as saying if they take the series, you take the absolute value, and it's still finite. That's what this definition says. Let's try to see some examples. Okay. Example 1. Sum n from 1 to infinity, negative 1 to the n, 1 over n squared. Okay. Well, number 1, is this one convergent? it's very easy to see this is alternating, right? And this one is decreasing, and the limit n goes to infinity, 1 over n squared equals 0. Therefore, this is convergent. According to the, let's say, yes. According to the alternating series test. Great. Is this one absolute convergent? Well, that means we take the original series, we take the absolute value, which gives you, now remember, before it's alternating, now the negative 1 to the n just disappear because no matter what, you get positive. Is 1 over n squared, if you take the sum, convergent? Well, it is because of p series. So yes. Therefore, this original series with a negative sign is convergent, and it is also absolute convergent. Okay. Now let's see the second example. What about this one? Number 1. Let's see. Number 1. Is it convergent? Yes, according to the alternating series test. Very easy to check, so you check by yourself. Number 2. Is it absolutely convergent? Well, you take the absolute value. It's not alternating anymore. Okay. Now, is this one convergent or divergent? You definitely know this is divergent because of P series, or you can say harmonic series. So the conclusion is this one is convergent, but it is not absolutely convergent, because before I take the absolute value, I was convergent. After I take it, I'm not convergent anymore. So I'm convergent, but not absolutely convergent. Okay, you see the definition here? Let's try a third one. N from 1 to infinity cosine n. Okay. Oh, let's not do this. Let's do cosine n over n squared. Okay. What is this? Well, it's going to be a sequence. It's going to be cosine 1 ingredient over 1 plus cosine 2 over 2 squared plus cosine 3 over 3 squared. Okay, and dot, dot, dot. Question 1. Is this one always positive? I doubt it, because cosine is between negative 1 and 1. Just by random luck, you will hit some number, and nothing is going to give you negative terms. Okay, so not positive. Number 2. Is this one alternating? Well, sometimes it's positive, sometimes it's negative, but there's no guarantee. It's always one positive followed by another negative, because these numbers are really random. They're not like a nice pi over 2 over n or something like that, which will give you some nice pattern which is alternating. Okay, so it's very possible that you have two positive and then followed by some random negative. So we have the trouble. It's not alternating, but it's not positive either. Is it convergent? Actually, we don't know. Because for anything negative, we can only have the alternating series, but this is not alternating either. So we don't know. But is it absolute convergent? Well, we just take the absolute value. give you this. Remember, n squared is always positive. Now, what do you know? You have a series. This series is given in this formula, and it's always positive. And as long as it's positive, we can use comparison test. Clearly, cosine n is less than 1. Before, you cannot use comparison test here simply because it's not positive. But now, after you take the absolute value, it is positive. Then we can say this. And clearly, this one is convergent by the comparison test. Because it's less or equal than 1 over n squared. Moreover, this one is positive. Therefore, it is convergent. So if we say this is convergent, let me take it back. The whole thing is convergent. Then it's fair to say this one is absolute convergent. Okay. Is it convergent? We don't know, but we do know it is absolute convergent. Okay, and we have the advantage that is once you change everything to be positive, you can apply integral test, you can apply comparison test because they only works for positive series, right? Okay, that is really great. Now what we want to say here is we can actually say it is absolute convergent, therefore it is convergent. We want to say if you can show it's convergent, it's already enough to show it's absolute convergent. Okay. In other words, if it's already absolute convergent, definitely before you take the absolute value, it is convergent. This is the theorem. Okay. So instead of saying we don't know, it is. And this is by the absolute convergence theorem. Okay, let's do it formally. Let's take a look at the theorem. Absolute convergence theorem. Okay. It's very simple. If a series is absolute convergent, then it is convergent. In other words, to show some series to be convergent, you just need to show it is absolute convergent, and then you are all set. Now go back to the examples. Do you know how to show if this one is convergent? I don't, but I do have a way to show it's absolute convergent. But by the theorem, once it's absolute convergent, it definitely is convergent before you take the absolute value. That's what the theorem says. Okay, very convenient. Then starting from now on, any series you have that may have a negative value, you just don't care. I just go take the absolute value right away. Then the series becomes positive. Now, once everything becomes positive, you can apply everything you had from integral test, test of divergence, and comparison test. And then you find, well, it's convergent. Then we say this series is absolute convergent because you took the absolute value and found it to be convergent. But after that, you can already say it is convergent without saying anything more because it's guaranteed by the absolute convergence theorem. Okay, why is it true? It's actually very easy to understand. I will give you two, I won't say proof, but just idea. Okay, why is that thing true? Why is this one convergent is enough to say this one is convergent before you take the absolute value. Let's consider two things. The first one is, let's say you have some series. Let's just take the 1 over n squared, right? This is the original sum an. Let me put it here. This is after you take the absolute value. You can see all the positive stay positive, all the negative become positive. Okay. Now what we're trying to say is, This one adds all the value up. Correct? This one add all the value up, except sometimes they cancel a little bit because you do have positive and negative terms. When you have a positive and negative terms all mixed together, they tend to cancel each other a little bit. Okay? Cancellation. Okay. Now on one side, you have all the value just keep going up. On the other side, the same value, but sometimes they cancel a little bit. Maybe they cancel a lot, maybe they cancel a little bit, but they cancel. Of course, the one with cancellation is going to be less than the one without cancellation in terms of value. If that idea makes sense, this one always add up. This one sometimes add up, sometimes actually minus, sometimes go down, but they have exactly the same value. Then, of course, the one on the right, which is after you take the absolute value, will give you a way bigger value. Okay. Then, if this one converge, it's enough to say this one converge. That's one side. Okay. If without cancellation it's convergent, then not to mention with cancellation it's definitely convergent. Another way to think about it is this. Let's take your original AN. Let's say we have AN sampled from things like that, and then maybe from exactly the sense here. So your AN is going to be sometimes positive, sometimes negative, maybe two positive together and then negative and positive. So it's not alternating. This is your AN. You sum all these together. Good so far? Okay, sometimes it's positive, sometimes it's negative. Now what I'm going to do is I'm going to take the absolute value of AN. That is means basically I keep all the points except if it's below, I move it to here with exactly the same length. Good so far? So this line here, you can clearly see it's actually absolute value of AN because it's always positive. Okay. Similarly, for this symmetric line below, you can very easy to show this is absolute value of AN with a negative sign, which means it's always negative. Good so far? Now, if sum n from infinity AN converge, that means if you put all these positive lines together, it's less than infinity. Okay. Now, if sum n from that is convergent, you can actually take the negative sign times the negative one, it's still convergent. That means if you sum all these lines together, it's also convergent. Good so far? Then what about sometimes you sum this line, sometimes you sum this line, sometimes you sum above, sometimes you sum below. It's definitely going to be convergent because all the red lines have no cancellation, all the black lines have no cancellation. But the green lines, which is the real one, will have cancellation. So it's definitely smaller than either the black ones altogether or the red ones altogether, which I have already proved they are both convergent. Okay. If you want to put it into algebra, it's very easy to see. Basically, you just use a simple fact. AN is less or equal than absolute value AN. Right? If it's negative, it's less than. If it's positive, they are exactly equal. Meanwhile, AN is definitely bigger or equal than negative absolute value AN. It's actually kind of in between. Then sum this, sum this, and sum this. Converge. Okay. This one converge because this is nothing but this one times the negative one. Then the one in the middle, what do you say? It's convergent. So the absolute convergence theorem is true. Okay, so I think that's everything we need to say about absolute convergence theorem. Basically, from now on, if you see any series, it's not always positive. Okay, sometimes it's negative, and you don't have alternating series test. What you can do is just take the absolute value and write it down. If you have a series, which has some positive, maybe some negative, which you don't know how to handle, you simply just take this one. Then everybody become positive. Then you can start to use integral test, comparison test. But once you prove this one is convergent, then you can say, hey, then this one is convergent because of absolute convergence theorem. So you don't have to actually worry about the original one, which you don't know how to do. Just like the example we showed for this cosine n here. Okay. You know it's negative, but it's not alternating. Sometimes it's negative. Then you just take the absolute value, apply comparison test, then it's all set. Sounds good? Okay. If that's the case, that actually gives you 3 more interesting terminologies. Convergent means if you take the sum, it's convergent. Absolute convergent means if you take the sum of the absolute value, it's convergent. Okay. We also know if its absolute value is absolutely convergent, it's definitely convergent. Okay. This is guaranteed by the absolute convergence theorem. Okay. Then it's possible that we have a series which is convergent but not absolute convergent. Because if it's absolute convergent, it will be convergent. Right? But it's possible. It's very possible. Starting from analogy, it's the same thing here. If you have cancellation, you have something finite. Now you remove all the cancellation, just put all the values together. Then it's possible that the new value, when you put them together, they become too big. Without the cancellation, they become bigger. It's possible that now they're too big, they become infinity. Okay, this kind of condition is called the conditional convergence. So let me say it again. Conditional convergence means convergent, but not absolute convergent. If you need example, check the example 2. Okay, this is the alternating series. It is convergent, but once you take the absolute value, it becomes a harmonic series. It's divergent. Therefore, when you take the absolute value, you make everybody positive, the value turned out to be too big. But if you start to have some cancellations, then the value will be small enough to make it convergent. Okay, so that's the first one. So far, so good. Now we want to introduce 2 additional tests, which is probably the most powerful test for series test. They are called the ratio test and the root test. For each of the tests, you check one thing. An analogy is very similar to each other. For the first test for ratio, you check an plus 1 divided by an. What I mean is, if you have a series, you have 1 plus 2 plus 1/3 plus 4, whatever. All you need to do is take the next one divided by the previous one. Take the next one divided by the previous one. You keep doing this. Then when n is big, you will have a ratio. And if the limit of this ratio is a constant, then the series is going to be absolute convergent if this L is less than 1. If it's bigger than 1, it's divergent. If it's equal to 1, nothing you can say. Try something else. That is what we call inconclusive. Okay? That is called the ratio test. The root test, we check a different thing. Limit n goes to infinity, the nth root of an. And then again, we are going to have a number. If that number is less than 1, absolute convergent. If the number is bigger than 1, divergent. If the number is 1, inconclusive. So you can see the conclusion part for both tests are exactly the same. You look at the number and check if it's less than 1 or bigger than 1. For the ratio, you check a ratio, which is the next term over the previous term. For the root, you basically check the ratio of the terms. You take the nth root, or you take the root of the terms, but you take the nth root. Okay. It's very vague. So let's try some examples. Let's try some examples which are simple. Okay. number 4. Let's check this one first. Okay, limit n goes to infinity. 3 to the n squared plus 1. Okay, what do you have? Well, it's always positive. And integral test, maybe not. Comparison test, maybe, maybe not. We really don't know. Test of divergence, you can easily see the bottom, 3 to the n, dominate the top, so this limit is going to go to 0. So it's not divergent right away. We run out of options. But now, with the ratio test, okay, we just need to check an plus 1 divided by an. And let's check. An plus 1 equals n plus 1 squared plus 1 over 3 to the n. An is just n squared plus 1, 3 to the n. Sorry, this is n plus 1. Now, for absolute value, since they are both positive, we can just remove the absolute value. And what we have is an plus 1 divided by n squared plus 1 divided by 3 to the n. And then I flip them. Okay. Keep going. You can see 3 to the n plus 1. What you have here is one more 3 left on the bottom. Okay. Now you need to think about, okay, what's the limit? Well, infinity over infinity. What's the leading term on the top? N squared. What's the leading term on the bottom? N squared. So together, we should have 1. With the 3 in the front, we should have 1/3 by leading terms. So let's recall, we took the absolute value, we checked the ratio. The ratio is the next term divided by the previous term when n is big. Okay. We end up with a number 1/3. Is 1/3 less or bigger than 1? Less than 1. Therefore, is convergent. Actually, it's absolute convergent by the ratio test. We'll write this down. You actually need to write down ratio because ratio roots, they all start with R. So, by the ratio test. Okay, kind of makes sense now. So basically, you check a ratio and try to see, yeah, if it's less than 1 or bigger than 1. If it's less than 1, go ahead and try to say it is convergent. Okay. Now let's check root test. What do we have? Okay. Number 1, if you take a look at this one, what's going to happen? Well, geometric, integral test, comparison test, alternating, you try all the stuff. It's pretty difficult. You have never done anything with n's power here with n in the middle. It's really difficult. Okay. But now you remember, maybe this is a good place to do the root test. Why? The root test requires to take the nth root. And you happen to have an nth power here. So probably that's a good idea. So let's try this. Okay, so what we have is we want to do limit. N goes to infinity. The absolute value of an. Oh, in my notes, did I put absolute value? I should have put absolute value. Okay. the reason we want to do root is when you take the nth root with nth power, these could just cancel each other, like the square root of square. Okay, nth power, nth root, they cancel each other, so it's gone. And this is 2/3 by leading term. Then is absolute convergent. According to the root test. Okay, this is what we have from the ratio test and the root test. We just check two things. The first one, you check a ratio. The second one, you check a root. Before we go ahead and do more examples, let's talk about why this kind of theorems. Why is it working? Okay, and why it's actually a really good tool. Let's take a look. Let's take a ratio first. This is a good test. Why? Because number one, you take the absolute value. So you don't care if it's positive or negative. You just say, take the absolute value, then everybody is equal. That is great. Okay. Second, an plus 1 over an equal limit n goes to infinity. Okay. Equals L. Then we say it's less than or bigger than, depends on L is less than 1 or bigger than 1. Let's take L to be 1/3, as in one example. What does it mean that an plus 1 divided by an is 1/3? That basically means an plus 1 equals an times 1/3 when n is big. Actually, it's not equal. It's almost like, but not equal, because we took the limit. Good so far? Okay. What do you mean by an plus 1 equals an times 1/3? Or in another word, what do you mean by the next term is the previous terms times 1/3? For example, 1, 1/3, 1/3 square, which is 1/3 times 1/3. 1 times 1 is 3 to the cube. The next term equals the previous one times a fixed number is nothing but geometric. Serious. Right? Then what are you trying to check when you do the ratio test? You're trying to say the next one divided by the previous one eventually become a number. So of course, if s less than 1, that means r less than 1, the common ratio less than 1, the geometric series converge. If L is bigger than 1, R bigger than 1, the geometric series diverge. Okay, so basically whatever you have from there is nothing but a direct corollary coming from a geometric series. That's pretty amazing. Plus, several good things. Number one, geometric series doesn't care about if it's positive 1/3 or negative 1/3, or sometimes positive and sometimes negative. Number two, you're not saying the original series is geometric series. Okay, you're just trying to say when n is big, this one behave almost similar, or like, or equivalent, whichever word you want to use, to a geometric series. Okay, let's take the example here. What's going on? Okay, basically what you're trying to say is this one geometric? Of course, this one is not geometric. Okay, because you have an n squared term on the top. Definitely it's not geometric. But when n is big, what's going to happen? When n is big, we took the limit of the next term over the previous term. We find it's almost 1/3. That means when n is huge, this one almost behaves as a geometric series with r equal to 1/3. Even though it is not a geometric series, it is similar to a geometric series. Then of course we check if this one is less than 1 or bigger than 1. Sounds good? Another way to think about it is this one geometric? Well, this part is geometric. This part is not. Now when n is big, the one on the bottom, which is the geometric part, become a dominant. Okay, the one on the top, yeah, n squared plus 1. Go to n plus 1 squared plus 1, which means you change to the next term. If you take the ratio, yeah, they are more or less the same. That's why the bottom become a geometric. This whole thing is not geometric, but very similar to a geometric. That's why this one works. Sounds good? Okay. If that is okay, what about ratio test? What if this one is 1/3? Okay. Now do you see the pattern? This basically means an is almost like 1/3 to the n, because the nth root of an is 1/3. Then an itself is 1/3 to the n. Now, of course, this one is, again, geometric. So what you're trying to do is, you're trying nothing but to compare the series you have right now, okay, to a geometric series and check the common ratio. Okay, so if you have something like that, you either do a ratio test or you do a root test. But what you really check is actually how similar is an to a geometric series. Okay, if you find them to be similar, you are going to have this L. This L is actually just the common ratio. Then, of course, you check if it's less than 1, if it's bigger than 1, and you will be able to say it's convergent or divergent. That's what we're trying to do with ratio test and the root test. Okay, enough talking now. Let's try some example. We already have 2 nice tools. Now maybe you want to get a little bit hint of when to use ratio and when to use root. Okay. Number 1, ratio and the root all take absolute value. So if you run out of options, you cannot, because you have negative terms, these two can be good candidate. Okay. Number 2, for ratio, there is a particular good one. That is factorial. Why? Let's take a look. Okay. To make it more clear, it's 2 times n factorial 5 to the n. Okay. My claim is whenever you see a factorial, you should seriously consider the ratio test. Let's see why. Limit n goes to infinity, n plus 1, n factorial become n plus 1 factorial, 5 become 5 to the n plus 1, times, remember to flip. Okay. What's good about this? The first good thing is 5 to the n, 5 to the n plus 1, you have one more 5 left. The 2 and the 2 cancel each other. Now what you have is n plus 1 factorial divided by n factorial. And that's the reason we want to do ratio test. Because ratio test will just make this factorial a little bit bigger. But now, using the fact, which we did several times in class, n plus 1 factorial is nothing but n plus 1 times n minus 1, dot, 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 all the way to 1. N factorial is nothing but n times n minus 1, dot, 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 all the way to 1. So if you take the ratio, a lot of the terms cancel each other. You will only have one left. That is n plus 1. Okay. So if you have factorial, you take an plus 1 divided by an, your factorial just have several more terms. The most of the terms, they cancel each other. That's great. Now what is this when n is big? It's infinity, for sure. What do you mean by that? That means the next term over the previous term is infinity. This term just gets way bigger, not to mention you want to sum them together. Well, you just need it to be bigger than 1. Therefore divergent. Okay, so when you see factorial, definitely consider it's a good time to use ratio test. Okay, it's not guaranteed it's always going to work, but let's be honest, so far you don't have any way to handle factorials. So maybe this is the only way. Okay, and the good news is about factorials, when you increase n to n plus 1, you just have several more terms. In this case, you only have one more term because most of the factorials, they cancel each other. Okay, even by looking at the original thing, you can actually guess what's going on. You're just saying, hey, if I increase n by 1, I'm going to have one more 5 from the bottom. I'm going to have n plus 1 from the top. This is roughly the ratio I'm looking at. That's exactly what the ratio test is trying to check. Okay, so this is going to be handy. Now let's take some ideas about, what do you want to check if you have ratio test or not. I think it's pretty obvious also, because why do you want to take a root? That must be because you have a power. Okay, so let's check this one. Do you really want to do the ratio? This is your a, n plus 1. And you want to divide that thing by a, n. Do you even know how to start? Okay, so that's why I say that ratio test probably won't work when you have a nice power. That's why we have two tests. Let's take the root test. Then you just need the limit. N goes to infinity. Okay. Number 1, definitely the root test. Number 2, the algebra may be tricky. Let's think about how we handle this. Try some examples, like what is the square root of a square square? It's going to be this, right? Okay. What is the cube root of a, let's say n equals 3, to the 3 square, which is nice? That is a to the cube, nice, which is a to the third. How did you get that? You get 3 from 9 times 1/3, right? Now you probably start to see the pattern. When you have a power, you have a root, you can actually transfer them into a power. It's nothing but this one to the 1 over n. For example, square root is nothing but 1/2 power. Cube root is nothing but 1/3 power. Now, when you have power and power, if you're not familiar with this, again, try some examples. What is 2 to the square to the cube? 2 to the 6. What is 3 to the 4th to the 5th? 3 to the 20. So what you do is you multiply these two numbers together. Then you just need to multiply n squared and n 1 over n together. Together, they give you n. Okay. Whatever that limit is, it's going to be your ratio. You want to check if it's bigger or less than 1. Now, up to here, just stare at it. It should look familiar. And what do you have? I'll recognize it's actually the definition of E. Okay, try to recall. And then E is 2.7, so bigger than 1. Divergent. Okay, so we have done so many different examples. But basically for this section, let's summarize what we did here. Keep in mind what we're trying to do is we want the series to have negative terms. Okay? Then what we do is we take the absolute value to make it all positive. We check if it's convergent. If it's convergent after you take the absolute value, then it's called absolute convergent. The good news is if it's absolute convergent, then the original one is automatically convergent. Good. A second important thing is there is a new concept which is called conditional. Hey, where is it? Oh, which is called conditional convergent. Basically, this is the one between convergent and absolute convergent. Absolute convergent is way stronger than convergent. Okay, and the conditional convergence is just right in the middle. Then we introduce two tests, the ratio and the root test. The idea comes from geometric series. Okay, you're trying to compare your existing series to a geometric series. The good news is you always take the absolute value in both tests, so you don't care about positive or negative. Once you have the geometric series ratio L, you just check if it's less than 1 or bigger than 1. Less than 1, convergent, bigger than 1, divergent, and if it is 1, inconclusive. One thing I want to mention is, like one example we showed, bigger than 1, it's very possible that your L is infinity. In our case, it's fine. Also, L can be 0. It's also fine. L will never be negative simply because you took the absolute value here. So L will be a number from 0 to infinity. And even if it's 0 or infinity, you still can tell which one is bigger or less than 1. 0 is less than 1, infinity is bigger than 1, so it's still doable. After that, we did a lot of examples. And the hint here is, in general, root test will be only applied if you have a power involving n. If you have a power involving n. Okay. Ratio test is the one which is more popular, especially when you have something like a geometric, if you have something like this, you take the n plus 1, it will cancel with this one and leave you only 1, 5. If you have factorial, it will cancel everything, leaving you only some terms. So an plus 1 divided by an will always give you something nice. That's why ratio test is actually probably the most popular one. Okay, finally, one last example. Sum n from 1 to infinity, negative 1 to the n, 1 over n. Like I said, this one is convergent by alternating series test. But what happens if you apply the ratio test? An plus 1 is nothing but negative 1 to the n plus 1, 1 over n plus 1. Limit n goes to infinity, an plus 1 over an, absolute value. Then after that, we don't have to worry about the sign. We just take the positive part. This is an plus 1. This is an. The answer is going to be 1 by leading term. Okay. Up to here, you should say inconclusive. Okay. Why? Because ratio test cannot tell the difference. We want something to be bigger than 1 or less than 1. If you are almost 1, that's when it gets really tricky. It really depends on, are you a little bit smaller than 1 and how small you are. Okay. In this case, it's smaller than 1, but almost 1. And it's small enough, so it's still convergent by the alternating series test. But the ratio test basically fail. Okay. That may be another interesting thing to see. That is, if I write down several terms, if you think about it. What do we have so far, right? We have sum. We can have a number. We can have a geometric term, which is a power. We can also have a term which has factorial. We can also have a term which is polynomial. Now, if you apply the ratio test, what's going to happen? With all the examples, and you can check by yourself, let's change this to before to stay out of confusion. Number 1, the an plus 1 is going to be this, and this, right? Then an plus 1 over an is going to give you every single term changed. Number 1, the 4 doesn't change, so they cancel. There's no 4 anymore. 3n plus 1 change all the way to 3n plus 1. Therefore, you have 1 more 3 left if you use this to divide by that. Use this to divide by that. Okay. This divided by that will definitely give you a factorial cancellation. Still okay? What's most interesting about this is actually the most polynomial term. This one and this one. When n is huge, Do you realize they share the leading term? Both are n squared. That means when you do ratio test, polynomial actually doesn't change the ratio at all. Okay, only the power and only the factorial change the ratio. If you just have n to the cube, that's become n plus 1 to the cube. Well, if you think about the difference between them, if you take the ratio, the limit always goes to 1. So if you have a polynomial, because it doesn't change the leading term, it doesn't change the ratio. So again, you're looking for geometric series. Okay, polynomial is probably too slow for geometric series because geometric series is exponential. So in order to give some significant contribution to the ratio, you need to have at least have something exponential. A power of n won't help, okay, according to the leading term, because the leading terms stay the same. All right, that's all for today.